Okay, so yeah, good. So 17.9, divergence theorem. As we said, it's basically the flux divergence analog of Stokes theorem. So it goes like this: let E be a simple solid region. Let me open the door. It's kind of hot in here. Oops. Okay. And let S be the boundary V. Be given a positive orientation. So that's you will have an outward unit normal. Okay. Let F be a C1 vector field on an open region containing E. And then the flux through the boundary surface, the flux through the boundary equals the integral of the divergence on the solid. Okay. Right, so that's the statement. And we should say that actually it doesn't have to be a simple solid region. In fact, any bounded region with a continuously differentiable boundary will do. Okay, so you might think, oh, Stokes, this theorem seems kind of limited. And you can only do it on simple solid regions. But in fact, what happens is that as long as it's a bounded region with a continuously differentiable boundary, you can actually chop it up into pieces, all of which are simple solid regions. So you can extend the divergence theorem to these guys. So it's actually more powerful than you might think. Okay. Okay, so we're just going to do some simple examples to see how this works or how this works. Okay, so here's an example of that it works. Okay, so let U be the unit ball in R3, and let du be the boundary, right, the unit sphere. X squared plus y squared plus z squared plus 1. Okay, and let f of x, y, z be 3x, 3y, 3z. Okay, and so let's just verify that the left-hand side equals the right-hand side. This example is sort of set up to be simple. So, but why don't I let you set up the integrals. Okay, so take a couple minutes and see if you can actually set up if you actually understand what these things are. So just remember how you calculate these things. Do you know how to do? You okay?
Yeah.
Yeah. I should have brought a mathematical movie or something.
We've done Flatland.
Flatland.
It was terrifying. I watched it over the weekend. I thought it was terrifying.
It's the one with the computer graphics.
Yeah.
Right. That one. Like when they kill when they cut that guy into pieces.
Yeah, it was really weird.
Yeah, that didn't happen in the original. Yeah. Actually, there was one done in 1964, like an early example of computer animation, and it's only 10 minutes long. It's very peaceful.
Try to find that one.
I have it on my Amazon account. So. Yeah. Okay, turn to somebody next to you and say what you're doing. Say what you've done.
Or did you just?
Are you doing the first setting? No, okay, right. Yeah.
It's a dot product, not a cross product.
Yeah, but
Yeah, so that would just be the partial x, comma, partial y.
okay.
Why did you have to parameterize it?
And then,
Why did you parameterize it?
and then dv, just.
Oh, yeah.
So just all the partials are against the original. Like partial x, partial y. What's the original?
Oh, that thingy is just partial x and partial y. That's exactly what it just is this.
In 3D,
Okay.
3 dimensions.
And then when you, like, it's not a real thing.
Right,
It's just
right.
an idea. And then when you dot it against it, you just get the partial f. You get the f sub x, f sub y, f sub z. Are your or like, yeah, it's the first
I just tried to.
first one of f with respect to x, first second one. I don't know. I think it makes sense.
Just
And
try
then
to
you
start
set up
on
the
the light side.
boundaries in spherical coordinates. Can you do that?
For the left side or for the right side?
For the
But yeah, but
For the
like
triple integral.
yeah, because oh yeah, that's what we've done.
And then for the double integral,
Oh, divided by.
I started out with r of x y equals x y square root of 1 minus x. I like try. I don't know.
Oh, you
the
tried
first
to-
one.
okay. Okay, yes,
I think that was right.
Yeah.
And then you just do f of r dot the cross product of the partials of r. If I remember this correctly.
Yeah, I just forgot.
XYZ cross.
And then do that
to
one.
study
Or-
these.
Yeah.
It's like an album. I'm just so happy it's my friend. Yeah, I thought it was going to be. I said, I'm been so hard. And once I gave us in my calculator class, I did CFC. And every midterm we got like this big front back to do whatever we wanted. Yeah, 3 midterms, and then at the end you could have 6 quizzes. Wow, because it's like 1, 2, 3, anything. Yeah. So I even had so many examples, and one of the examples
Okay,
was
so
and I just.
so what do you do? Which one? Does anyone want to say anything about either side? Yeah, Flo.
So for the left side, for the double integral.
Okay. Yeah.
I started with a parametrization of the surface,
Okay.
which I did x comma y comma square root of 1 minus x squared minus y squared.
Let's see.
Okay. Right. So. Mhm.
Yeah, and then I found the cross product of the partials of that, which is 2x, that radical thing, comma 2y, all that stuff, comma 1.
2x.
And then everything in the radical.
2y. Okay.
And then you set up the integral, the double integral over the surface of f of r, which is 3x comma 3y comma 3, everything under the radical.
3x, 3y, 3y. Huh?
And then dot that against the cross product of the partials. dA.
Right.
And then I would solve that using polar coordinates.
Okay. 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 Yeah. So that'll do. Yeah, Sarah.
Don't the twos cancel out?
Don't the- In when you do this thing.
Yeah, I think it's just X. Like,
I don't know. I actually haven't done it. But you can check. We can check. So partial with vector x is going to be 1, 0. So 1 over 2 square root of
That's true.
negative 2. Right.
yeah.
So the 2's cancel out. Y. So 1, negative 4.
Forgot my differentiation was.
You cross them, you get negative x, no,
That's very
you get x over 1 minus x squared minus y squared. You get y over 1 minus x squared minus y squared. And you get y. Which you could, when you, if you multiply this thing through by, what happens when you normalize this? This thing here is your z, right? This is z, right? So basically what you have is x over z, y over z, 1, right? So when you normalize it, remembering that actually x squared plus y squared plus z squared equals 1, then you end up actually with x, y, z. Right? Because this is x over z, y over z, 1, right? And if you'd like to make this thing have norm 1, you can multiply the thing through by z, and then now it has no 1. So xyz. Well, you could also think of this as just xyz.
I didn't do my differentiation right. That's cool.
No, that's okay. That's okay. So, yeah. So basically, what you're doing is you're integrating 3x, 3y, 3z against xyz. So you're taking the dot product of those guys, ds, over the surface. Yeah, look.
Why? Wait. Can you explain again why that just comes out to be x, y, z? Do you just multiply everything by z?
I'm sorry. If you normalize it, if you
Okay.
normalize it to get the unit normal.
Okay.
To get the unit normal. Get the unit size. So, yeah. And then looking at it that way, actually, you can see that what you're doing is you're integrating 3, right? You get 3x squared plus 3y squared plus 3z squared, which is just 3 ds over the surface. Right? Is that right? Yeah, that's right. Which is what? If you integrate the number 3 over the surface, what do you get? Just to avoid the polar integration that Flo was going for. What do you get? You get the surface area. So what's the surface area of the ball? Oh, you don't know? It's actually 4 pi. So 4 pi r squared is surface area of a ball of radius r. So you get 3 times 4 pi r squared. So you get 12. Okay. Did you get that, Sue? When you did?
But I didn't end up finishing it.
Oh, okay. Oh. Okay. Okay. Then the other side, right? So the other side is maybe easier. Right? What's the divergence? 9, right? You take partial of this, right? dx partial. This dotted against 3x, 3y, 3z, and you get 3 plus 3 plus 3, 9. Okay. And so you end up with 9 times the volume of the ball, right? Right, so, and what's the volume of the ball?
4/3 pi cubed.
4/3 pi r cubed. So 4/3 pi r cubed. And you see we get 12 pi. So, just an example to note that it actually works. So the next one I think will be the last thing you do. Last exercise. Here's the divergence theorem. To calculate the flux of negative x cubed, negative y cubed, 3z squared across the boundary of this thing u, which will be points in R3 where x squared plus y squared is less than 16, and z is between 0 and 5. Okay, so you're asked to calculate the flux across the boundary of this object. Of course, you're going to use the divergence theorem instead of working out parameterizations for the boundary of this thing. You all recognize that you see what this thing is. What is it? Z is between 0 and 5, right? So it's chopped off between two planes, and it's a cylinder. So you've got this tube of radius 4, and it's chopped off at height 0 and at height 5. Right. So you could do this by taking the flux through each of these surfaces, right? Through the top, through the bottom, and through the sides. But instead, we'll invoke the divergence theorem and say, okay, well, all we need to do is calculate this.
Is it supposed to be triple as well?
Yes, thank you. I was thinking maybe we'd have time to watch Flatland, the short Flatland video, but maybe we'll do it some other time. Okay, so take a minute and just set up and start the integral. Okay, so let's do it. What do you get? You're taking dx dy dz plotted against -3, negative x cubed, negative y cubed, dz squared. And so you end up with, of course, negative dx squared minus 3y squared plus 6z d. Okay. And then how do you integrate this? How would you integrate this? Yeah.
Switch to cylindrical coordinates.
Cylindrical coordinates, right? It's a cylinder, so let's switch to cylindrical coordinates, right? So this is going to be r dr dz d theta, theta dz, r dr dz. This thing turns into negative 3r squared plus 6z. Right? And z ranges from 0 to 5, theta ranges from 0 to pi, and r ranges from 0 to 4. And then, from there on, it's just, you're back in calculus 2, and you end up with negative 725. Okay, so that's it. So that's the end of the course. Yeah, congratulations on making it to the end.